morning, everybody. My name is Mauro Bernardi. I'm from the Department of Statistical Science of the University of Padova, and the paper I will present to you today is a paper on fast Bayesian model selection algorithms for linear regression model, and it is a joint work with Manuela Catelan from my department and Claudio Dusato from the Department of Statistics of Florence. The general framework we will consider in this presentation is that of a Gaussian linear regression model where the continuous outcome y is regressed on a set of covariate x, and we consider the case where p, the number of covariates, is larger than n, the number of observations. We include the prior distribution on the set of regressors, and we consider the Dirac spike and slab prior of George McCulloch 1993 that postulates a mixture of a spike, a Dirac spike that puts mass in 0, and a slab component, which is a Gaussian component for the non-zero elements of beta. The inclusion variable gamma tells us which of the two components are selected. The model specification is completed by assuming the following prior on sigma squared, the scale of the model, which is inverse gamma, and the inclusion probability theta, which is beta. The major computation issue we face when we want to explore the posterior distribution of competing models is that evaluating the variance, covariance matrix sigma gamma star, which is made of two major components, the square of the design matrix X and the inverse of the prior distribution. So when P is large, we need to invert a high-dimensional variance-covariance matrix. Moreover, in order to evaluate the probability of including a new model on the set of exploratory models, we need to evaluate the marginal likelihood, and the marginal likelihood required to evaluate the S gamma star square quantity, which is a square that involves the posterior variance-covariance matrix sigma. So we need algorithms for fast and efficient exploration of the posterior distribution of the competing models, and those algorithms require the evaluation of the inverse of the variance-covariance matrix and the likelihood function. One of those algorithms that allows to update the inverse of the posterior distribution and the inverse of the variance-covariance matrix is the Sherman-Morrison rank 1 update. For a dimension of the parameter space equal to p gamma, the Sherman-Morrison rank 1 update requires 6 times p gamma square operation to add a column and 2 times p gamma square operations to reduce the set of covariates by deleting one of them. So let us introduce a little bit of notation. We denote by x tilde gamma the augmented design matrix obtained by stacking the true design matrix x gamma and the inverse of the prior variance covariance. The new augmented design matrix is obtained by stacking the current design matrix by column and the new column we want to add to the design matrix. We call the new column by XU, and we denote by XU tilde the new column of the augmented design matrix. So the idea is to update, to find algorithms to update the inverse of x tilde square and the likelihood. Brown and his co-authors suggest to use the QR decomposition of the augmented design matrix x tilde gamma. We instead relies on a different version of the QR decomposition, which is named thin QR decomposition, and which provides a unique reduced QR decomposition on any full column rank matrix A in such a way that A can be obtained as a product of Q1 and R1. R1 coincides with the R matrix of the full QR decomposition without the last n minus p rows, while the Q1 is a submatrix of the Q matrix by considering only the first p columns. So we employ the thin QR decomposition of x tilde gamma in order to update the inverse of x tilde x. There is several reasons that motivates the use of the thin QR decomposition instead of the full QR decomposition. The first reason is that the QR decomposition requires the updating of the Q matrix and the R matrix, and when the dimension, the space P gamma is large, the computation of those matrices require a lot of computational effort. While, moreover, the QR decomposition requires the storage of the Q matrix, which is a very big matrix when P is large. Finally, we observe that the Q matrix is not needed to update the variance, the posterior variance covariance, because the posterior variance covariance matrix sigma gamma can be obtained as the square inverse of the square of the R matrix. So our idea is to provide algorithms to track the QR decomposition of X gamma instead of the full Q decomposition in such a way that the sigma can be obtained as the square inverse of the square of the R1 matrix. So if you consider the first algorithm is concerned to the update of the X gamma matrix when a column is included, a new column is included in the set of covariates. We would like to find a matrix R1 that is such that Q1 times R1 is equal to the original X tilde matrix. So R1 is the thin R decomposition of the X matrix, X tilde matrix. If you look at the Wilkinson diagram in the example, when P is equal to 7 and P gamma is equal to 8, in order to update the R matrix to get the new matrix, we only need to update the last column of the new R matrix. Our algorithms provide an efficient way to calculate that column. And in particular, that column can be calculated by regressing the new XU tilde matrix, the one that we add at the end of our augmented design matrix, against the space spanned by the previous design matrix. So by running that regression, we end up with the column we need to update the R matrix. When we move to this problem, to the problem of removing the kth column, the computational task is a little bit more involved. You can see from the Wilkinson diagram, in the example when P is equal to 7 and we want to remove the third column, that removing the third column requires the deletion of the third column of the original R1 matrix, the deletion of the last row, and moreover, we need to zero all the elements along the main diagonal of the R matrix. Our algorithm provides an efficient way to deal with that task, and in particular, we can see that the new matrix can be obtained by multiplying the previous matrix R1 with the complete set of given rotation that zeros the elements along the main diagonal of the previous R matrix. Once those multiplication has been performed, the new matrix is obtained by deleting the kth column and the last row of the resulting matrix. So our formal proposition prove that the matrix that you obtain by performing those multiplication and those deletion coincide with the matrix you obtain by applying the ThinQR decomposition to the new matrix X gamma, X tilde gamma star. Okay? So if we go back to the evaluation of the marginal likelihood, we see that the evaluation of the marginal likelihood may relies on the evaluation of the S gamma star square, which is a square that depends on the posterior variance covariance. But if we perform some calculation, we easily see that S gamma star square depends on the inverse of the matrix that is the inverse of the R1 matrix. So L, in this case, is the inverse of R1. And if we look at the posterior variance covariance, we see that also the posterior variance covariance depends on the inverse of the R1. So both the likelihood and the inverse of the posterior and the variance covariance matrix depend on the inverse of L. So if we would have some algorithms that allows us to directly update the L matrix, we save all the computation that are required to compute the inverse of the R. Indeed, we have found those algorithms. Let's consider again the case where we want to add a column as the last column of our design matrix. In that case, we only need to compute the last column of the L matrix. And that column can be obtained again by regressing X, U tilde on the set spanned by the previous regressors. Okay? When we move to the problem of computing the new L matrix, when a column is deleted, the computation task is a little bit more involved, in the sense that it requires the computation of all the columns from the kth one to the last one. Those columns can be obtained from the previous columns, or the previous L, the corresponding columns of the previous L matrix, times the set of given rotation that are required to zero the elements along the main diagonal of the R matrix, and then by deleting some rows or some columns. What is important now is to observe that the new L matrix is obtained by multiplying the previous one by the set of given rotation when found by considering the elements of the R matrix, but we don't have the R matrix, we have the L matrix. So if you look in more detail to what is necessary to compute the set of given rotation, we need to compute all the elements along the main diagonal and all the elements along the diagonal above the main diagonal of the R matrix. As concerns the first diagonal, it is quite easy to calculate the elements along the main diagonal of the R matrix starting from the corresponding elements of the L matrix, because they are the inverse of the other, while for the elements above the main diagonal we have some problems, because we not only require the elements above the main diagonal of the R matrix, but we need the elements on the main diagonal of the R matrix as modified by the set of given rotation that zeros the previous elements. So the problem is quite involved, but we found an algorithm for computing those elements. And the good news is that the algorithm is the number of floating point operation of that algorithm is linear in P minus K. So I conclude my presentation by showing you this table that summarizes the computational cost of performing adding or deletion of some column on the R matrix, on the R matrix, on the QR authorization, on the Sherman-Morrison rank 1 update. From our calculation, you can see that the exact computational cost for performing the modification of the L matrix is less than those required by performing the same computation on the R matrix. Moreover, the computational cost depends on the distance between K and P. Okay? So it depends on the position of the column that we are deleting. So thank you very much for attending the presentation. I remind you that if you want to discuss something about my algorithms or about Bayesian model selection, you can contact me on the platform we have in the conference, or you can email me. So thank you again for attending the presentation and enjoy the conference.